Picture a sky filled with machines moving as a single, flawless organism. Right now, the pinnacle of autonomous warfare looks like a perfectly synchronized drone swarm, executing complex maneuvers under the continuous direction of a single command hub. This hive-mind perfection relies on an architecture called centralized training and decentralized execution, or CTDE. During training, a centralized critic collects every piece of data from every single drone to figure out the optimal strategy. To make this work, standard algorithms like QMix require a constant heartbeat of communication. In this network graph, the central hub streams continuous updates to the swarm, calculating joint action values so every drone knows what its neighbors are doing. Researchers perfected these models in highly observable simulation environments, like the massive multi-unit battles of StarCraft II. In a digital sandbox, the algorithm easily solves complex coordination tasks because it assumes perfect, uninterrupted connectivity. But this digital perfection hides a fatal flaw. The entire system is built on a mathematical concept called monotonic factorization, which demands that all those data connections stay intact. If that tether snaps, the logic falls apart. And in a modern conflict, that unbroken line of communication is exactly what an enemy targets first. Out in the physical world, the airspace is dominated by electronic warfare. Terrestrial arrays and radar jammers blast the electromagnetic spectrum with noise, creating massive communication denial of service zones. When that invisible energy rips through a drone swarm's flight path, the central command link is violently severed. The machines are instantly deaf and blind to each other. Deprived of its global data feed, an algorithm like QMix shatters mathematically. It simply isn't designed for isolated, continuous action spaces. Without a constant flow of rewards and shared states, the drones lose their ability to solve cooperative tasks. The monolithic swarm collapses into a collection of confused, solitary robots. To keep these machines functional, we have to stop trying to protect the central brain, and instead design a multi-agent system that actually thrives in the dark. Look at a single drone drifting inside this jamming field. It is entirely alone, cut off from the swarm. This isolation triggers a massive issue in reinforcement learning, known as a non-stationary environment. Because its teammates have vanished, a search tactic that worked perfectly yesterday suddenly fails today. From the drone's perspective, the rules of the physical world appear to be randomly changing. Standard learning models react to this failure by immediately punishing themselves. The drone registers a negative update to its expected utility, its Q value, and actively erases its previously successful tactics. It unlearns how to survive. Engineers prevent this using hysteretic Q learning. This split-screen chart illustrates a deliberate asymmetry. Instead of treating all data equally, an alpha rate quickly integrates positive experiences, but upon failure, a much smaller beta rate shrinks the penalty. It is a state of engineered optimism. By minimizing the impact of negative feedback, the isolated machine protects its vital tactical heat maps. It retains its optimal search paths, weathering the chaos of the severely degraded environment without forgetting what works. But individual survival is only the first step. Eventually, two of these optimistic, isolated machines will randomly cross paths within the jamming field. When they do, they execute a concept called the epidemic protocol. Originally developed to manage database servers at Xerox PARC in the 1980s, this rumor-mongering protocol has been resurrected for delay-tolerant, opportunistic networks. Rather than trying to ping a dead central hub, the drones rely on extreme physical proximity to execute a split-second data handshake. They compare their local queue tables, spreadsheets mapping action coordinates to expected utility. Executing a maximum valuation overwrite, they select only the highest values between them. Dropping failures and keeping successes, each machine instantly learns optimal tactics that kept the other alive, requiring zero centralized processing. Through this opportunistic infection, rogue units begin to function as a decentralized collective. Every random encounter strengthens the tactical intelligence of the agents involved. Now scale this dynamic across a massive 100-kilometer by 100-kilometer domain, completely saturated by electronic warfare jamming. As these isolated drones continue to drift and intersect, those localized handshakes ripple organically across the theater. Optimal tactics spread exponentially from agent to agent, behaving exactly like a viral transmission. The original intent of the jamming blanket was to kill the network by destroying the central command. Instead, this grid map shows how the electronic void acts as a catalyst, forcing the swarm into a delay-tolerant biological entity. This viral topology bypasses tactical nap entires must abandon the tether of a central command. True resilience comes from distributed, headless architectures that take the isolation designed to destroy them and weaponize it.